This should be better as a recording because you'll actually see my face instead of the bottom of my beard or whatever's been showing up in these other videos. Okay, let me share the whiteboard here. Whiteboard. We're recording to the cloud. Okay, cool. Okay, so let's see here. So what we're going to do is we're going to talk about some of these energy problems. So here we go. So I got one. So I'm working off of homework 12, old homeworks. The problem with some of these, of course, is you guys don't have this textbook. So I'm going to work this. I have the textbook, so I'm just going to draw the problem out for you. So this is a 7.44 from the old textbook, which was Elgar, LeBray, Crow, and Roberson. Anyway, so let's see what we got here. Here. Okay, so it looks something like this. It tells you, okay, this is given. Okay, it's water at 10 degrees C, flowing at a rate of, let's see, 0.35 cubic meters per second. And it is assumed that the head loss, okay, they give us the head loss ahead of time, which is awfully nice, 2v squared on 2g, or at least they give us an equation to calculate it. From the reservoir, okay, from reservoir to the gauge, okay, where v is the velocity in the 30 centimeter pump. So I'm going to put a little v30 on here. What power must the pump supply? Okay, so required, we want to know the power the pump must supply. So W dot pump to the water. Let's see, I'm going to erase this. All right. Oh, they also say assume alpha equals 1.0. Okay, which is awfully nice when we get something like that because it's just going to make our lives a little easier. All right, so now I'm going to do the drawing of kind of what's going on here. So we've got a reservoir. And then it looks like they kind of drew like it has like a nice curved entrance. This is how they like to draw pumps a lot of times. Something like this. This thing is kind of rounded like that. It's, and then it's going to kind of go up. And it looks to me like they're trying to say that this pipe just kind of keeps going. So normally the way we would draw that to say that it just keeps going is we kind of draw it with like a little, one of those little doohickeys. Okay. Now there's a little gauge right here. So gauges, for some reason, tend to mess up my class. It's just an easier form of manometer. Instead of having to work a manometer equation, we've got a gauge, and the gauge actually tells us what the pressure is. So P equals 100 kPa right here. Okay, and then we've got this kind of floating here. And so they kind of give us some elevations. So Z equals 6 meters right here. Z equals 10 meters right here. This is a 30 centimeter pipe. This is the pump has an elevation of 2 meters. This is a 40 centimeter pipe. Okay, I think that's the whole problem. Okay, so, excuse me, it's a rainy day out there, so we're, so it's made me sleepy. Okay, so we're going to do the, in some ways this should be obvious that it's an energy problem because we're in the energy section and that's kind of what we're working on. But, assuming that that's not so obvious, what gives us away right off the bat is that the thing we're looking for has something to do with a pump. So that should tell you right off the bat that the only way to get it, like the energy that a pump is supplying or anything like that, is you know, it has to be this. So so let's see. So we're going to do so energy equation. So P1 on gamma plus Z1 plus alpha V1 squared on 2G plus HP equals P2 on gamma plus Z2 plus alpha V2 squared on 2G plus H of the turbine plus the head loss. Okay. A note real quick on the head loss, just because I always like to, you know, mention this even before we get into it, is that there's going to be losses. So if we go from, so if I draw my control volume and I say, well, this is my in right here, or my one is really the surface up here. Okay, and my out is going to be right here. Okay, because we know information right there about the pressure right there. So I'm just going to call this 2. Okay, between those two, you know, where are we losing energy? Well, we're losing energy here at this entrance. That's called a minor loss. And then we have friction losses along the walls of this pipe here and all along the walls of this pipe. Right? I'm not going to draw both lines, but okay, they're also what we call minor losses at these bends. And I think that that's it. Okay, there's almost certainly, you know, losses inside the pump, but we don't account for those because the pump is just kind of it's kind of like, what is the pump doing in net, right? And maybe adding a whole bunch and it's losing some energy as well because there's, you know, mechanical inefficiency, but all that just goes into the pump. We just want to know how much the pump needs supply to the water. Okay, so right now what we're looking for this. Okay, so so let's go ahead and start kind of thinking about terms and what do we know. Okay, one thing to note too, it always bears repeating, especially when we get a number like this, is 100 kPa. What does that mean? 100 kPa means 100 kPa above atmospheric. Okay, so it doesn't say it, but if you don't hear anything, assume that that's a gauge pressure. Just because I don't know, that's just what we normally use. Like when you measure your tires, you know, you've never measured your tire. Like if your tire had no air in it at all, you would put the little gauge up to it and it would, you know, the little thing that slides out, it wouldn't slide out at all. And you would say it has a pressure of 0. It doesn't actually mean that it's, you know, absolute 0 pressure in there. It means it's atmospheric pressure. So almost all of your gauges usually work in gauge pressure. That's why we call them gauges. Or maybe that's why we call it gauge pressure. Anyway, okay, so let's go from these points here. So point 1, and that's important to keep in mind though, because if this is gauge, then it means that point 1 is atmospheric, and I can go ahead and say it's 0 because it's atmospheric, right? If that 100 were, and this one becomes, you know, this one becomes 100 kPa over gamma, which in this case is 9810 Newton per meter squared cubed, right? And that's because, I mean, yeah. So, yeah, if this were absolute right here, and I wanted to plug in the 100 for atmospheric pressure, I have to put in 101.3 kPa. But we don't want to, you know, ideally we keep our lives simple. So assume it's gauge, which it almost always is. Okay, Z1, well, the elevation there is 6 meters. So we use green and go down here. This way I don't lose things. And then V1, of course, is 0 because it's a tank. Okay, and then we've got an HP, which is what we're looking for. Okay, and then let's see, Z2, we're going to pump it up to 10 meters. And then alpha V2 squared on 2G. Well, the alpha can go away because we know that it's 1.0. So we're not going to worry about that. But we need to get to V2, which I guess is a good time for an aside over here. V2 equals Q over the area 2. So let's go ahead and get that right now. And then we'll come back to filling out the rest of this equation. So V2 equals Q, which is 0.35 cubic meters per second divided by the area, which is pi over 4 times the diameter squared, 0.3 meters squared. Okay, so let's see what we get there. 0.35 Oh, got to turn it on. Let's see. Let's start with the pi. Pi divided by 4 times 0.09. Put that on the bottom. Multiplied by 0.35 equals 4.9515. V2 equals 4.9515 meters per second. Okay, so we'll go ahead and plug that in over here. Let's say plus, so this is going to come down as 4.9515 meters per second squared over 2 times gravity, which is 9.81 meters per second squared. Okay, we'll note that there is no turbine. And then we're going to get to head loss. And they say that the total head loss for the whole system is this. Of course, it should be obvious it's a little oversimplified because somehow, even if we were ignoring all what we call minor losses, which are these bends and this entrance, clearly, there's got to be something in here for this section of pipe, but it doesn't matter. We're just going to take their word on it because this is a class and we're learning, right? So let's go ahead and just do it. So we're going to add 2 velocity and 30 pipe, which happens to be this velocity, 2 times 4.9515 meters per second squared over 2 times 9.81 meters per second squared. Oh, sorry, this needs to be squared like that. Okay, so there we are. And let's see. So I'm going to go ahead and simplify some of this. Notice that these two right here can be combined into one term. That is 3 times that v squared over 2g. A lot of times you should look for that in your problem just because it's going to save you a little bit of time in your calculations. I'm going to keep it separate for now just because. So I've got 6 meters. Well, you know what? I'm going to go ahead and combine that 6 and that 10. So I'm going to say HP equals, let's see, 100,000 divided by 9810 equals, so this is 10.194 meters, plus this is going to be 4 meters. And then let's do 4.9515 squared divided by 19.62. Okay, this is going to be plus 1.2496 meters plus, and then we'll multiply that times 2 and we'll get 2.4992 meters. Okay, so again, I always like to think in terms of, what is this pump doing? This means basically it's taking water, it's raising it 4 meters. Okay, it's pressurizing it by this much, and it's giving it this much velocity head, and this much is being lost to friction. Okay, so I always like to stop and kind of just think about this in terms of, energy, which is, not something that a lot of the problems ask us to do, but to me, it just kind of makes sense. So in this case, like most of our energy basically is going to pressurizing the water. Okay, so it'd be nice if we didn't have to do that, but perhaps this was set up so that we get 100 kPa right here. And maybe it's because this pipe stretches for like a long way, and this pressure is going to drive the flow, wherever it's going to go. So there's a lot of times there can be good reasons to have that pressure. Of course, if you have a leak, then you're going to lose a lot of that. So, anyway, so let's add all this up. So 10.194 plus 4 plus 1.2496 plus 2.4992. Okay, so we get 17.9428. So HP equals 17.943 meters. Okay, so now to solve this thing at the very end, and hopefully, based on what I did last time and what I'm doing this time, hopefully this should be like coming into focus or whatever, that the work, this is the W dot to water, okay, or pump to water, okay, is going to be gamma HPQ. So W dot to water, and I only put this little to water because it helps me keep track of what's what. 9810 newtons per meter cubed. HP is 17.943 meters, and Q is, let's see, from right up here, 0.35 cubic meters per second. So W dot to water equals, let's see here, 9810 times 17.943 is 0.35, and we get 61,607, 61,607. And let's see here, meters cubed, cancel the meters cubed, and I'm left with newtons meters per second, which is a watt. Okay, so W dot to water, the rate of work or power equals 61.6 kilowatts. Okay, this really, for these problems, is about as straightforward as they get. I mean, I guess sometimes they'll just ask for, instead of asking for W dot pump to water, sometimes they might just ask how much head does the pump supply? That would be an even easier problem because we wouldn't have this extra step over here. I've certainly given ones like that on tests, and usually the rationale being, I just want you to show me you know how to use the energy equation, and then you know, I'm not too worried about this for now, and you know, another problem is harder or longer or whatever, and I just want you to kind of do a quick problem. Okay, so one last thing before I move on from this. One of the reasons you might want the water in the pipe pressurized, for those of us who live in New Orleans, and I think this is becoming more common around the country too, is we get a lot of boil water advisories. You guys may have noticed this. I don't know what neighborhood you live in, but you know, all neighborhoods seem to get them these days. And this pressure inside the pipe can be really important. And I think that this is the way that they're running these pipes underneath our streets. Is, I mean, it's something to think about, is that pipes do have leaks, right? And underneath the ground out there, we've got two pipes. Like I've never built a house, but I know they exist down there. You've got one main pipe coming in that's bringing you your water, and you've got a pipe coming out that's taking away your sewage. Okay, and they both have leaks, right? And that should be that's a little bit terrifying when you think about it. You're like, wait a second. So I've got a pipe right here. It's got the water I'm going to drink in it, and right next to it, I don't have brown as a color, but you know, you've got this water leaving that's, you know, got like, you know, it's poop water, right? It's wastewater. So it's what comes off you in the shower. It's what comes out of your, you know, when you wash your hands or wash your dishes, and it's when you flush your toilet, right? And so it's this disgusting water, and it's leaking, right? So I don't care where you live, it's not perfect, right? Now I'm not saying that it's a tremendous amount of water, but there are leaks because these pipes are not perfect and they've been down there for a long time. There's no reason to expect that they are. I mean, ideally they would be. If it was enough to like percolate to the surface, you would know because it would stink, and you would call somebody and hopefully they would fix that. And one of the important things about these, maybe, and I'm pretty sure this is in their design, I haven't taken these classes in a while, is that you want air on top of these. And one of the reasons you want air is because things break down more efficiently when there's oxygen. So as this, you know, sewage or this brown wastewater, as it moves through this pipe, is exposed to this air, and that kind of allows the aerobic bacteria to do their work on the sludge to some extent, or on the nasty stuff to some extent. Now, this water, on the other hand, is pressurized. And you'll know this because every now and then one of these will bust, and when it does, it blows a hole in the street, right? But the reason it's pressurized is because basically if you've got this, you know, if the atmosphere, so you imagine this right here, more or less is at, let's say it's at atmospheric pressure. But let's suppose this here is at 100 kPa, so 100 kPa above atmospheric pressure. So I'm imagining kind of like, you know, a situation like this. Well, then what's happening is when there's a leak here, right, there's a pressure gradient that's causing this water to flow out. right? So even though there is this nasty green water out here, it will not just keep on going this way and get into your pipe because your pipe is pressurized, right? So as soon as it mixes with this, or as soon as it kind of runs into this blue water, it's going to kind of turn and flow whatever direction the blue water is flowing, because the blue water is flowing basically down the pressure gradient. Okay, so it's basically flowing from high pressure to low pressure. Okay, so it's like a force balance. And so what happens is, the reason we get a boil advisory is because something happens. Maybe there's a bust in the line somewhere or whatever, and this pressure drops. Maybe it drops from 100 kPa down to like 10 kPa or something. So then they tell you, well, there's still no reason necessarily why this water would flow into here. But what they say is, we just don't know. So they give you a boil advisory and they say, until we get the pressure back up, we want you to boil this water that's coming through your pipe just as a precaution. Whereas they like to say now, in an overabundance of caution, which I find just like the most ridiculous expression, whatever. Why don't you just say caution? Caution is an overabundance of, being careful. Anyway, that's just me. So anyway, so that's the idea. That's why we get these boil advisories. If something happens, we lose pressure. It could either be because a hole busts in this thing, a pipe somewhere. It could be because, whatever's pressurizing, whatever pump is doing it has busted. So just something to kind of be aware of. Okay, so any questions on this one? Hopefully you guys would interrupt me. You guys should know that you can. Okay, so let's do another one. Let's see here. Let's clear all drawings. Clear all drawings. Okay, so I'm going to do 7.45 from the same book. And it looks like this. We may end a little early today. Problem is, what we're doing right now is called simple energy, and it's hard to do simple energy problems. The textbooks don't have a bunch of them. I don't have a bunch on hand. Anyway, because we really want to get into the more complicated ones. Okay, so this one is much more like, I think I might even given this one on a test at some point. I love angled pumps and things with manometers. And again, this is my favorite type of problem, because it means that you know your geometry. You know your, okay, this doesn't look like a 12-inch and a 6-inch, but just bear with me. Obviously I'm not a very good artiste. And then we've got a manometer coming off of this sucker. It goes like this. You guys know how I love manometers. Actually, that last little bit's a little bit off. Oh no, that was such a good curve. I'm trying really hard right now. And that is like as excellent as I've ever been. Okay, so you guys are seeing me at my absolute best. So when you write a review of this course and you're like, man, he sucked and he was at his best, then that's fair. Okay, so here we go. So this distance right here, 46 inches. What a horrible amount of inches for them to give us. First of all, they chose to do it in inches, and then they give us 46. So it's not even like a nice, 48 would have been so easy and nice. These are a bunch of jerks. Let's just all agree that, whoever wrote this is a jerk. Okay, so the flow rate is, let's see, Q equals 6 CFS. And they also decided to be a jerk by saying this is oil, which has an S of 0.88, 0.88. Okay, calculate the horsepower. Let's see here, required, the horsepower. Oh no, it wants horsepower. Okay, be very careful, it wants horsepower and not the head of the pump. Okay, so what that means is they want the power. It says calculate the horsepower the pump supplies the oil equals question mark, and they want that in horsepowers. The pump supplies the oil if there's a differential reading of 0.46 inches of mercury. So this is mercury. Okay, and at this point, hopefully you guys have kind of figured out that mercury has a specific gravity of 13.55 or 13.6. It just kind of depends. SHG equals 13.6. Just depends on your source and how many sig figs you want to use. Assume alpha equals 1 at all locations. It's really nice when they let us just assume alpha equals 1, because that means we don't have to do a bunch of Reynolds number stuff. Okay, so I'm going to make this point again real quick. I kind of sort of made it last time. But as far as when you can use the Manometer equation, so these things are, there's streamlines in here that basically look like this. Okay, the Manometer equation, because we're gonna use that, but it helps us pick our points. It tells us information about a point right here and a point right here. Okay, because those two things attach to our manometer. So that's our 1 and that's our 2. Okay, now the key here is, and the reason I drew those streamlines is that when you exit the manometer, you need to go at a right angle to your streamlines. That's the only way this can work, because the hydrostatic equations work in, static fluids, and they work at right angles to streamlines. Okay, streamlines that are not curving. Okay, at least that's as best I understand it. I think I worked this proof out one time, but I'm not going to subject you guys to that. But anyway, so you can't just decide that this manometer is measuring up here or like straight up. I mean, it's totally academic at this point whether or not I put 2, say, right here. I mean, whatever. That would, for this class, that would be fine. Of course, I can't even erase it now. But I have had people in the past put their points all the way up here, and then everything gets confusing because your manometer doesn't measure up there. Okay, so just something to be aware of. Okay, so let's go ahead and okay, once again, we see this thing right here. We want power. So if you want power plus, sorry, this is a pump right here in the middle, P. Okay, usually pumps look like this when the pipe comes in one side and leaves the other. That's what a pump looks like in the drawings. In real life, of course, they have all kinds of different designs. I'm not a pump expert, but I've seen a handful of them, and every one of them looks different, or all the ones I've seen have been different. Okay, so we've got a pump, and so we're going to go from 1 to 2. So again, it's better to think about this as in. So here's my in, here's my out. Okay, and we'll say, okay, P1 on gamma plus Z1 plus, did they give us anything about how much higher this is? They didn't give us anything, okay. Plus alpha V1 squared onto G plus HP. And by the way, pumps are a lot more common than turbines. That's just the way it is, at least in the problems. I don't know about in the real world. I would think probably in the real world as well. But I don't think that survey has been done. Mathematically, of course, they work exactly the same. Just one's on the right-hand side of the equation, one's on the left. Okay, so this one's a little bit interesting because we're gonna, first let's just see what we can get rid of. We can neither get rid of P1 nor P2 because it's within the pipe. Okay, this is something that a lot of my students want to do, is they want to get rid of these basically because they just don't like them, right? And of course, that's always nice, but we can't really do that. Z1 and Z2, we can't get rid of either of them either, unless we do something like, and for simplicity, I like to do this sometimes. I like to just kind of draw a line like this and draw a line like this. Call that distance between them H. Is perfectly fine. Just pick a letter, whatever letter you want. And so that means that I can make this my datum. Okay, or I can mentally say, well, Z2 minus Z1 is H. So mathematically, I can plug that in by bringing Z1 over to the right-hand side. But, it's kind of nice to go, well, this is my datum, and this is H, lowercase h. Okay, so that can work. V1 and V2, we can't get rid of neither of those because it's moving in both cases. So this is getting a little bit annoying, okay? And then HP, well, that's what we're looking for. And then there is no turbine, well, that's good. And this is one that my students will struggle with. So usually I will tell you this on an exam. There's no head loss between 1 and 2. And that's really just an assumption because it's like not that far between 1 and 2. So it's not that, in reality, there is head loss because we've certainly got, walls along here that, there's certainly friction there, but we're going to go ahead and assume that there's no head loss. And it's just because this is an assumption. And it's just because it's short, and there's no information. Like, there'd be no way for you to solve for that. So we're just going to go with that. So this equation is quite nasty at this point. Okay, so what we're going to do, and I do this all the time in my things, is I start solving for these things using other equations. So P1 and P2, those are the pressures. So what we always want to do with pressures is we want to say, okay, well, let's just do the manometer equation. And to do that, I need some more geometry. So I'm going to draw another line here. Okay, well, if I'd drawn it right, it would go right through that meniscus right there. Okay, and I'm going to give that a letter. I'm going to call that capital H. I don't know why. I think I've seen it in enough of the textbooks have just done it that way. So I'm just going to do it that way to, make things, I don't know, whatever. It doesn't matter. You can call it whatever you want. Okay, so let's do the manometer. I'm going to kind of squeeze it in at the bottom left, assuming I have space, which I probably don't. But at this point, I've done so many manometers that hopefully this is like making some sense to you guys over here. So I'm going to start at P1 and I'm going to go down. So I'm going to add gamma. That's gamma the oil. Okay, because remember, I drew those lines in blue, but this is oil. Gamma oil, and I go down H. Okay, now I'm in the mercury. So now I'm here. And we go from the mercury down here. So I'm going to add gamma Hg times that 46 inches. 46 inches. Okay, 40. What? Somehow I got yellow. Okay, 46 inches. I'm going to go ahead and divide that by 12. So I can get feet. So we're just going to do 46 over 12. 46 over 12 feet. So that gets me over to about here. And then I'm going to go minus, because now we're working upwards. And I'm going to go up this much. So 46 over, so this is in oil, gamma oil. Okay, we're going to go up 46 over 12 feet. And then we're going to go up H. And then we're going to go up lowercase h equals P2. Okay, so let's see. Gamma oil H right here, this gamma oil H is going to cancel with this negative gamma oil H right here. Okay, and that's why they almost never give us this. Okay, it's because it always cancels, almost always. Almost always. Okay, this particular H right here, okay, we used it up here in the energy equation, and it always cancels with this H right here. Okay, so just kind of like, if you watch, it's inevitable. So anyway, so I'm going to bring the P1 over to the other side. So I'm going to subtract this P1, bring it over here, minus P1. And then I know what I want to do is I want to divide that by gamma. So in this whole equation up here, we should note that this is gamma oil, because that's the oil that's flowing. So we want to divide this thing right here by gamma O. And when I do that, I end up with this. This is gamma oil. This is gamma oil. So I divide that whole equation by gamma oil. Okay, because that's what I want to plug into my equation. So that becomes, well, these gamma oils go away. Like this and like that. Okay, and this becomes gamma Hg over gamma oil. And if I work up through that, this becomes, so that gamma Hg becomes SHG over gamma water, and the gamma oil becomes S oil gamma water. Okay, and that's just from the definition of the specific gravity, right? Or the definition of specific weight. Either way you want to go with that. So these gamma waters will go away. Okay, so I'm going to go ahead and rewrite all this over here. So SHG, which is 13.6. over SO, which was 0.88, okay, times 46 inches over 12, excuse me, 12, so this is feet, okay, minus 46 feet over 12 minus H. Okay, so if we plug all that into a calculator, which is really the cleanest way to get this, 13.6 divided by 0.88 times 46 divided by 12 equals that number minus 46 divided by 12. Okay, so I'm getting 55.409, 55.409 feet minus h. Okay, there may be an error in there, but it looks okay. Okay, so that says that P2 minus P1 over gamma oil equals this right here. Okay, it's a little sloppy because I chose to squeeze it in at the bottom. Just holler if it doesn't make any sense. So what that does is I can bring P1, so like up here, my top equation, P1 over gamma, I can subtract that from both sides. So I can make this thing right here, P2 minus P1 over gamma oil, right, like that. Okay, so this quantity right here can slide into there. Okay, and that's kind of the game plan. Okay, so for V1 and V2, oh wait, I forgot, right? We can get rid of these alphas because alpha is 1.0 as assumed. Okay, so for V1 and V2, I'm gonna go ahead and erase that because that's just, for V1 and V2, we're gonna do continuity. So we'll say Q equals V1 A1. Okay, so let's see here. Q is 6 CFS equals V1. Oh, that's what we're looking for. And A1, which is pi times the diameter, which is 1 foot squared on 4. Okay, so V1 equals 6 times 4 divided by pi. Why can't pi just be a number like 5? Who built circles this way? Every time a pi shows up, gives you an, oh, what just happened? Okay. All right, there it is. Whew, that was close. I bet y'all were worried. 7.6394. 6394. That's feet per second. Okay. Now we don't have to do this again for V2. You can if you want. I leave that up to you if you like. But hopefully you guys are starting to see that if this is double that, okay, which is the case in this case, then the velocity over here is going to be 4 times the velocity over here. Okay, so so I'm just going to take that 7.6394 whatever and multiply by 4, and I get this number. So V2 is just a quicker way to do it: 30.558. 30.558 feet per second. Okay, so it looks like we have everything we need for this equation up top. Okay, so let's start plugging it in. Let's see here. So V1 squared over 2G. So that's going to become 7.6346394. Really is annoying keeping 5 sig figs, I must admit. I created this rule, and I admit that when people do it, their work comes out a lot better. So I'm pretty happy with the rule, but it sure is annoying. Okay, plus HP equals this P2 minus P1 over gamma naught. So we're going to take this quantity right here. So that's going to be 55.409 feet minus H. Okay, and here we've got an H right here. So we're going to add that H. So there's that. I was guaranteeing this was going to cancel, and it does. Even if I can't spell the word cancel. Cancel. And then we're going to add this V2 squared on 2G. So this is 30.558 feet per second squared over 2 times 32.2 feet per second squared. Okay, so let's see what we got here. Okay, I'm just gonna start plugging these numbers in the calculator. Let's take that 7.66 whatever, square it, and divide by 64.4, and we get 0.90622. 0.90622, that's feet, plus the head of the pump, equals 55 point. Okay, those H's go away. And then plus, let's see, 30.558 squared divided by 64.4 equals 14.500 feet. Okay, I wanted to make a point real quick before we continue. Notice, okay, and I didn't do it this way, but you could have done it this way. I think so notice that a comparison of these velocity heads. Okay, notice this velocity head is really, really tiny compared to this velocity head. Okay, such that like you could almost even say, well, like this one doesn't even really matter, like in the grand scheme of the problem. Okay, it's 2 orders of magnitude smaller than the change in pressure, and 1.5 orders of magnitude, whatever. It's super small. And I didn't do it this way. So down here, when we were calculating these velocities, I said, okay, well, look, this one, I said, well, okay, this one is this, but then the pipe is, the pipe loses half of its diameter. So its area goes down by a factor of 4, so its velocity is going to go up by a factor of 4. So I just multiply by 4 to get this. So if I go up here and I square that factor of 4, right, this is going to become 16 times as big as this. Okay, so I could have taken that 0.90622 and multiplied by 16, and I would have gotten this value right here. Okay, so it's just something to be aware of, that, when you're trying to think about how much things matter, how is important is it in this problem that I get this smaller velocity? Usually it's not very important. I mean, it depends on the ratio of the diameters of the pipes, but it doesn't take much. In this case, it's a factor of 2 for the pipes, becomes a factor of 16 in the heads. Okay, so just something to be aware of. So again, what's the energy coming into this system? Well, we've got a little bit of velocity, and that's really all the energy we have coming in. So we add a pump to raise the energy of that, that velocity head a bunch, but also to pressurize it a bunch and to raise it. Now, the raising of it is not really clear where that, the raise came from, because these values kind of all disappeared. But we did raise the water as well. So let's go ahead and solve for that HP. Okay, I'm gonna get rid of these little lines, which don't even mean anything to me. I don't remember why I wrote them. And that was like 8 seconds ago. So anyway, I'm gonna take that. So we're gonna add 55.409, and we're gonna add that 14.5. Okay, so we get 69.003 feet. Come on, give me a little feet mark. Okay, and so this problem, they wanted the power in horsepowers. Okay, so let's go ahead and erase a bunch of this junk just to give myself some space. Okay, so to get that in horsepowers, let's see. So this is the power that's going to the water. Okay, to the water. Okay, because this is the head that was added to the water. So we're going to say gamma HP Q.
Is it to oil though? Right.
Oh, yes, thank you. To oil, right. To the oil, to the fluid, to the oil. Which is actually a really nice thing that I'm glad you said, because this is a good spot where I always forget to put, like for this gamma, it's like, I'm like, once I get this number, I'm like, all right, I'm home free. And I turn my brain off. And I always forget that this gamma, if we're pumping oil, it's a different gamma, right? So we need to do 0.88. So equals 0.88 times 62.4 PCF. The HP, which is 69.003 feet, and the Q, which was 6 CFS, something like that. Okay, so W dot to oil. Okay, the power to the oil is times 6 times 62.4 times 0.88 equals 22,734. 734. And again, we check our units. So we've got cubic feet right here, canceling with this cubic feet on the bottom. So I got foot-pounds per second. Foot-pounds per second. And then W dot to oil equals, so we just divide that by 550. That's the conversion. And we get 41.3 horsepowers. The only nice thing about horsepowers is that it's much easier unit to write out than this. But other than that, it's horrible in every way. It's also, I guess it's also like, it's easier to say, well, how much power do we need to supply? Well, 41.3 horsepower is a lot easier than 22,700 foot-pounds per second. Because, I'm going to forget that number immediately. So the only other, these problems have all kind of worked the same way. And that's pretty common. One time I did this on a test where, and it created a huge, I guess, I didn't intend it as a trick problem, but it kind of came out as if it were a trick problem. But what I did is I gave people the horsepower that was applied that the pump was supplying. And so if I gave you the horsepowers instead, well, you would take the horsepowers, divide by 550, and maybe I was asking for the pressure at 2 or something, right? Or I don't know what I was asking for. Maybe I wanted the flow rate, and that was not given, right? I don't remember what I was asking for, but basically, instead of this, I said, okay, well, here's 41.3 horsepowers. So, multiply by 550 to get the power in foot-pounds per second, and then plug everything into this equation and pull out the HP, right? And then you have this, and then you can plug that directly into this equation. Okay, and then solve for whatever it is the question was asking. I never think of it as a trick question when I ask for something different. To me, it's, this is what engineering is, right? You have an equation, solve for one unknown or the other, but just be aware that that's a possibility. Of course, this could also, instead of being horsepowers, if it was in the metric system, it would be, megawatts or kilowatts or whatever. Nice thing, of course, is in the metric system, it just comes out in watts and we're happy with it. We don't have some other imaginary horsepower unit because, stupid horsepower units. Okay, let's see if I can find one more that I like. Okay, let's do this one. Any questions?
Yeah, so power to oil. So that's like basically the power that the pump is given out to towards point 2.
Is given out to what?
Like towards point 2. Like after.
Yeah, so it's what it supplies. Yeah, so basically like right here. Yeah, that's a good way to look at it.
Okay.
I mean, it's supplying it right here, right? Because the pump clearly does not, is not touching the water at point 2. But yeah, that's a good way to look at it. If I were to look at the total energy of the oil, right? So the oil would be cruising along with the same amount of oil, the same amount of energy. It would hit this pump, and then we'd have a huge burst in energy, right? And then it would go this way until it got to point 2. Does that make sense?
Yeah, that makes sense.
Okay, so what we're actually going to do really, really soon is we're actually going to keep track of energy precisely that way. So I'll let y'all watch the video because it's next week's topic. But really, so let's imagine there was friction in this pipe. So what would actually be going on, if I do this in kind of like green, is that like we would be slowly losing energy. So this would have a downward slope. We'd be losing energy until we hit the pump. And we'd just be losing energy due to friction. And then all of a sudden we hit the pump, and we would actually, our energy, if we keep track of our energy in terms of head, would actually go up by 69.003 feet, like this. 69.003 feet of head would be added. And then once we get to the other side of the pump, we're going to lose energy again. Okay, because again, we've got friction along here. Okay, And so that's really the way to think of it. So I mean, it's a really excellent question. You're like kind of leading us right into where we're going next. The other thing is, and just if I may say so, we lose energy faster on this side than we do on this side. And the reason for that is because the pipe is narrower. And so if the pipe is narrower, then, and so there's two things. One, the amount of friction we lose depends on how fast it's moving. It depends on this, v squared on 2g. So the faster it's moving, the more energy we lose. And so the water's moving faster over here just because the pipe is narrower. And so because of that, we're going to lose energy faster. So the slope of this line would be like steeper than the slope here. Okay, but that's something we'll kind of get to. But if I can say that right now.
Is that some function of like the surface area to volume or something like that?
You mean the fact that we lose energy faster?
Like to friction and stuff? Yeah.
Yeah, so there's two reasons we're gonna lose it faster. One is just the faster it moves, like why do we lose more energy per foot of the pipe if it's moving faster? Because like I'm trying to think of an analogy for just like when you're sliding a block across a table or something, right? Because when in that case, the force is constant. But of course, the faster you move it, the more energy you're going to lose to that friction because it's going to, I mean, you can imagine how much it's going to heat up, right? So I'm trying to think about why exactly that is. I'll have to think this. I feel like this should be something very obvious to me, but I'm brain farting right now. So I'm just going to go with, I don't know.
That's all right. It's all right.
Okay. Yeah. But you guys both look so happy that I don't have that answer. Anyway, so we'll think about that. So this is called this thing will be called the energy line, the energy grade line. And it's basically, you keep track of the energy through the whole system. And we do it on, we have very specific, there's good reasons to do that. And like people will draw the energy grade line for an entire piping network. They're just trying to, figure out, I assume, just keep track of where do we need a pump, what's going on, where are we at risk of cavitation, et cetera, et cetera. So yeah, this is a really beautiful screen. I hate to delete it, but there we go. Clear my drawing. Okay, so I'm gonna do this one. This one's out of that same textbook. It's 7.46, and they keep giving us the discharge, which is fine. So here we've got, but I like this one because I've assigned this one before, I believe, but also it's got a turbine, which turbine's a little bit rare. Okay, and then let's see, Q from this thing is 480 CFS. Okay, and it's going like this. And they like to have turbines like this. They like to draw them like this. And then the water just kind of like dumps out. Okay, so then they give us some geometry. 30 feet. This is a diameter of 7 feet. This distance is 5 feet. So clearly not to scale. Okay, what power? Okay, so we want, in this case, and I'm going to draw it a little bit differently. I'm going to draw the power output from the turbine. So W dot from turbine, and not from the water. Okay, that's the required right here. Okay, it gives us the efficiency of the turbine. It's 85%. Okay, it's always good to just go ahead and convert that into a decimal. And the overall head loss is 1.3 V squared on 2G, where V is the velocity in what they call the penstock, which is this pipe leading up to the turbine. Okay, assume alpha is 1.0 at all locations. Okay, so the only one point I want to make here, overall head loss. Okay, so this is an interesting thought, and I don't love I would never assign this question for this reason. So basically, the water is, so this is the idea, what we're looking at right now is the idea behind a turbine and behind a reservoir, right? You dam up the water, so you get, a nice amount of head right here, 30 feet of head. So this would be a pretty small dam, but whatever. And then you put a turbine down here, and you try to remove as much of that energy as possible using the turbine. Okay, the question here, and the reason that I don't like this, is it says the head loss here is 1.3 V squared on 2G. Okay, now if this were a Bernoulli problem, I couldn't do Bernoulli from, say, right here, location 1, to right here at location 2, because there isn't really a streamline that follows that. I could kind of draw something that I would call a streamline, but really what happens is if I were to ignore the head loss from this water falling out here and losing all of its energy as it like slows down, that would be like, to me, that would be a gross, like that would just be ridiculous. So I wouldn't want you to do Bernoulli from there to there. However, they give us a total head loss, and what they don't say in the problem statement is whether that head loss includes this drop and this loss when the water mixes right there. We're going to go ahead and assume that it does, because if it doesn't, well, then we can't really do much with this problem. Like we could, I guess we could like, we could put our point 2 right here maybe. Because we want to know something about the turbine. So our points have to be on the opposite side of the turbine. Okay, so the turbine has to be between points 1 and 2, or else it's not in our problem. So we can't really do anything with it. So we're going to assume that this expression for that total head loss goes from 1 to 2. Okay, I don't particularly like it, but what do you do? Okay, so let's go ahead and solve. Okay, and I may put I'm going to put my master over here in case we need any other equations, which seems likely. So here's P1 over gamma plus Z1 plus alpha V1 squared on 2G plus HP. Luckily, there is no pump, so we can go ahead and get rid of that. Equals P2 on gamma. That's what happens, you get better at writing this equation. You start canceling things before you're even done writing it, which is probably getting things a little bit out of order. Alpha V2 squared on 2G plus HT plus the head loss. Okay. So let's see what we got here. Okay, Z1. Well, we got 35 feet. Oh, wait, sorry, P1. We've got no pressure. Okay, because it's atmospheric. Sorry, I always forget the first time I taught this, I would just say in words, I would scratch something out and I would say atmospheric and then move on. And then people would look at their notes and they would come to me later and say, how did you get rid of that? So I realized it's important to say, well, we're getting rid of this because it's atmospheric. Okay. Z2, well, that's the datum. At least I'm going to make it the datum. You can make your datum whatever you want, but that's the one that makes sense to me. So Z1 will become 35 feet. Okay, we have no velocity at either location. So this fact that alpha equals 1.0, we're not even going to use. Okay, we've got a turbine, and that's kind of what we're looking for here. And we've got a head loss, which is this number right here. Okay, so let's go ahead and simplify this equation. 35 feet equals HT plus the head loss. Okay, and again, just for my own thing, we're ignoring minor losses, okay, what we call minor losses. And you'll see why we call them minor losses soon, which is right there. It's not that they're minor. In fact, usually there's a pretty significant loss in energy right at these entrances and things, but usually compared to the length of the pipe, it's small. Like the friction on the pipe per foot, we don't really lose very much, but usually you've got a lot of feet. So, so for this head loss, we're going to put in 1.3 V squared on 2G. Okay, so again, you can see, energy equation, right? We've got 35 feet of energy going in. We're going to take as much as we can out of with the turbine, but we still have to deal with the fact that we're going to lose energy. Okay, so basically, a lot of engineering is how do we minimize this so we can get as much of this as possible. right? Because we want that turbine, we want that power to power our homes or, whatever it is we want to do with that power, because we're power hungry, trying to take over the world. This would be where, if I could draw a nice picture of the brain, the mouse, not an actual human brain. Okay, so let's figure out what that velocity is. Velocity equals Q over A. Hopefully we're at this point getting pretty good at this, and we're realizing as soon as we see, velocity, if we need, we know, okay, well, 480 CFS divided by the area here, which is going to be pi times that diameter, 7 feet squared over 4. Just as something I'm just going to go ahead and throw out there, because every now and then this happens, is I get these issues where all of a sudden I give somebody a pipe that's not a diameter, not circular, because almost all the pipes are circular, but I give you like a square conduit. Remember, if you have a square conduit, it's not going to be pi times the diameter squared. It's going to be length times width. So just be aware of that. Again, I think people think it's a trick question because I, just do something that I haven't done before. So 480 times 4 divided by 49 divided by pi gives me 12.473. 12.473. That's feet per second. Okay, again, I always like to kind of, my master equation, and then the thing that I'm gonna the asides, things that the asides are the things that I forgot to do before I solved the master equation. Okay, so now we're ready, right? So we're just gonna say, well, we got 35 feet equals HT plus 1.3 times 12.473 feet per second squared over 2G. Well, 64.4 feet per second squared. Okay, just because I don't feel like writing the 2 times. It's amazing what can feel difficult. Give yourself enough time. 64.4. Okay, and we multiply times 1.3. And this whole thing is it's very close to pi. Okay, so basically we don't lose a lot of energy in this one. So this whole thing is 3.1403. So it's not really a lot of energy that we're losing here. So then the HT is HT equals that number minus 31.860. Feet. Okay. So then again, to solve this, okay, so I want to know the, I'm going to start with the work dot from the water. Okay, so gamma, H turbine, Q. Okay, we've done this now at the end of most of our problems. Okay, so the gamma of water in this case is 62.4 PCF. There's a point right there. The head of the turbine is 31.860 feet, and the Q is 480 CFS. Okay, again, we always check our units. The cubic feet here cancel with the CFS there, and I get pounds feet per second, although I prefer foots because it's more fun. It's like deers and shrimps. Okay, well, shrimps just are tasty, and shrimp are good, but shrimps. Okay, 62.4 times 31.860 times 480 equals some massive number, 954,000. Okay, let's just go with 5 sig figs. Okay, and that's foot pounds per second. Okay, now this is where I always like to think about this efficiency. In the video, I give you the formula for the efficiency. But so if I'm pulling out of the water 100, how much of that do I get to keep? If I have an efficiency of 85%, well, am I going to get more than 100 or less than 100? Well, I'm going to get less than 100. Okay, so to get that means I need to multiply by the efficiency to get how much comes out. Okay, so that's how I always think about it, right? So basically, it's always going to be the way that makes me least happy. So, so we're going to take this number and I'm just going to multiply by 0.85. So that's going to give me the W dot to user or from turbine to user equals this number times 0.85 times 0.85, and we get 81,130 foot-pounds per seconds. And usually from turbine to user, usually we divide by 550 to give us 1,470 HP. Okay, and that's rounded to 3 sig figs. So that's how you do these problems. And what we're going to do, any questions? So I'm going to, because I got 5 minutes, I'm just going to kind of briefly tell you how this gets harder, briefly. Okay, so what's going to happen here is that this head loss is going to get split in two. Okay, one of these is going to be the minor losses. And all of these look like this. K times V squared on 2G. Okay, and basically what's going to happen is you're going to look up something about this entrance, like something about its geometry in a chart, and that's going to tell you what this K is. And then it's going to tell you, well, which velocity do I use? Do I use the velocity over here or the velocity over here? It's going to tell you which velocity to use. Now, in this case, you know, velocity over here is 0 and the velocity over here exists. So I can tell you for an entrance, it's going to be on the other side of the entrance. But sometimes it'll be something like a contraction, like you'll have some, you know, a pipe doing this, and you'll have a velocity over here and a velocity over here. And you're like, well, okay, I figured out the K from the chart, but now I need to know which velocity to use. And the chart will tell you which velocity to use. I have to find that page number in your book, but there is one in your book somewhere. There's one in every book. Okay, for the friction along these pipes, okay, so basically you're going to add up. So for this, you're going to add up all of the minor losses. Okay, and then you're going to add to that the friction losses. And in a pipe, the friction loss looks like this: F, L on D, V squared on 2G. Okay, now the V squared on 2G, that's obviously the velocity in that pipe. I mean, it doesn't make sense that it could be anything else. The length, this is the length of the pipe. This is the diameter of the pipe. And then this friction factor is very hard. Okay, so everything was like, it seemed like everything was like cooking along just fine. And this friction factor comes off of a chart, which is called the Moody Chart. Okay, and that's going to be the subject of, well, I think next week we're going to do HDL, EGL, and then we're going to come back and we're going to start doing this stuff. But the Moody diagram is fairly difficult. So basically F depends on the Reynolds number, and it depends on the relative roughness of the pipe. So what you were just saying, Paul, so it depends on the ratio of the roughness elements on the pipe. So like if you've got a pipe and it's got a little, like, it's supposed to be made of concrete. So you imagine we've got little roughness elements, you know, which have a characteristic size to them, right? They may be millimeters, they may be inches. I mean, inch, you know, if you had roughness elements that were like an inch or more, like that'd be pretty big. But, or you might have like glass, which has basically almost no roughness. So you've got this and you want to compare that kind of as a fraction of the total diameter here. So different books call this roughness height something different. Just for now, I'm just going to call it X. That's not what it's actually going to be called in your book. Your book is either going to call it epsilon or KS. I can't remember. I've taught this out of a few different books now. But so it depends on these two things. Okay, this is called the relative roughness. So how big are the roughness elements relative to the diameter of the pipe? And then what is the Reynolds number? Okay, and that goes into this Moody diagram. And if you know to these two things, it can be really easy. But sometimes you have a problem where what you're solving for is this diameter. And unfortunately, the diameter goes into both the Reynolds number calculation and the Reynolds relative roughness. And so it creates this like iterative process, which is really annoying. And unfortunately for you, you probably need to know how to do it for the FE. But fortunately for you, down the road, when you become a professional engineer, you're just going to have a program that is going to iterate for you. So, which depending on who teaches you as you move forward, they may teach you how to write a code that'll do that in your calculator. Not with this calculator though, and not with any calculator that you can use on the FE. So make sure that when we do this iterative process, it makes sense to you, because you only get these like kind of weak calculators on the FE, and you get the Moody diagram. So make sure you understand it. So it's the first time that things get a little bit, it's the first time I think in your engineering education where things get really kind of sloppy, and you're gonna have to guess, which, you know, people are like, how do I guess what F is? And I'll walk you through that, but we'll do that in the next couple of weeks. Anyway, any questions, guys? Okay, well then I guess we'll call it a day. And yeah, so.
Sounds good. Thank you.
Okay, thanks guys.
Great. See you.
Okay, see you. Of our own, oh, gone. Okay, let's stop this thing. Recording, halt.